Ну, нам, видимо, сбились на кривой.
Вот. Теперь похоже на то, что и звук. Вот. Теперь похоже на то, что и звук. Okay, so let's start our first lecture. Of course, in the beginning of the course, I want to start with some organizational stuff. So first of all, you can see already the grading scheme for the course. So we have, of course, lectures on Mondays, seminars on Fridays. The grading scheme is the following. We're going to have a written midterm after the third module. It will be 30% of the total grade. There will be 4 quizzes. So the plan is the following. After 3 or 4 seminars, we're going to have a quiz with 3 or 4 problems. So essentially covering the materials that we discussed on the seminars. There will be a cumulative final exam at the end of the course. Well, cumulative means that it covers all the material of the course. So the weight is 40%. And if you want to get some extra 10%, you can just attend the seminars. And on the seminars we're going to solve problems. You can just go to the blackboard, solve the problem, and if you say solve 3 or 4 problems during the semester, it will be 10%. Say if you solve 1 problem, maybe this will be extra 2.5%. So something like this. So this is the grading scheme. Now I want to recommend several textbooks. So of course the classical textbook, introductory textbook on commutative algebra is Atiyah MacDonald. I start with this book. So this is called Introduction to Commutative Algebra. So the second textbook is actually my favorite textbook on commutative algebra, at least of the introductory level. This is Altman and Kleiman, a term of commutative algebra. So these are 2 introductory textbooks, and if you want to find something which is not covered in these 2 textbooks, I recommend you to look into the following 2 books. So there's a book by Matsumura, Commutative Ring Theory. So it's a relatively short but very dense book. There are a lot of additional stuff that we won't be able to cover in this course. And finally, the last textbook that I want to recommend is the book by Isomorphism Commutative Algebra towards with a view towards algebraic geometry. So the first textbook is translated into Russian if you prefer to read Russian books, and also the last textbook also translated into Russian. These 2 don't have translations yet. Okay, so now let's start actually the material of the lecture. So we're 20 minutes late, but anyway. So the first chapter I'm going to call Ideals and Radicals. Well, I can as well call this the basics of commutative rings. So we're going to discuss several quite elementary questions, but useful. They're going to use these ideas later in the course. So the first section is the maximal and prime ideals. So maybe I start with the definitions. Well, maybe before I even do the definitions, I start with the convention. So what we have in this course is the following couple of conventions. So first of all, I'm going to assume that R is of course commutative. So So whenever I use ring R, I mean a commutative ring. So in this commutative ring, I assume that, well, R is not 0, so 1 is not equal to 0. And 3, any ideal I in the ring R is proper, meaning that I is not equal to R. Okay, just 3, I would say, quite natural conventions. Now, with these conventions, I'm going to start with the definition of a prime ideal and maybe a maximal ideal. So an ideal. So for prime ideals, there is a tradition in commutative algebra to call them little p or maybe little q. So an ideal p in the ring R is called prime if we have the following property, that whenever x and y is in this ideal p, so the product of two elements in the ring is in the ideal, then this implies that x is in the p or y is in the p. Definitely you've seen this definition before. So equivalently you can say that p is prime if and only if the quotient ring is a domain. So these are prime ideals. Now let's recall maximal ideals. So an ideal, now for maximal ideals, if you want to follow the standard convention, you use little m. So an ideal m in the ring R is called maximal if the following is true. Well, this maximal in very natural sense. If you consider m sitting inside some other ideal, and this is sitting inside a ring R, so this is any ideal, then from this you can conclude that m is actually equal to I. So it's not possible for a maximal ideal to find ideal which is larger than the given ideal in the sense of the inclusion of ideals. So quite natural definition. And property, so if you have this property for prime ideals that the quotients are domains, for maximal ideals we have the following. So m is maximal if and only if the quotient is a field. Okay, can you give me an idea how to prove this? That ideal is maximal if and only if the quotient is a field.
If there were not unity in the quotient, we could construct a proper ideal in the quotient ring. So and there is a bijection between the set of ideals which contain one by which we have quotient and ideals in the quotient ring.
Yeah, that's exactly right. So the idea is to use the Correspondence Theorem which I assume you know, at least in some form, maybe as an exercise from the core algebra course. It says the following, that there is a bijection so whenever we have a situation, we have a ring, ideal, and the quotient ring, then there is a bijection between ideals of the quotient ring. Now, I is any ideal, and ideals of the ring R, but with additional property that they contain this given ideal I. Right? So in the idea for this bijection is quite straightforward. You have a canonical map, let's call this map pi, to the quotient ring, and whenever you have, say, an ideal J sitting inside the quotient ring, now you can construct pi inverse of J. This will be an ideal in the R, right? And clearly I is contained in the pre-image of this ideal. Of course, we can check immediately that the preimage of any ideal under any ring map, say I call this map F, this will be from R to S, and if I take, say, ideal J in S, I can consider preimage. That's something, some subset in the R, but this you can check that this is an ideal. So preimage of any ideal under any ring map. So maybe I write this as preimage F inverse of J. Is an ideal. So quite elementary but useful statement. Well, you need to check that, for example, this thing is closed under taking sums and taking products with any element in the R, but both these observations are quite straightforward. Okay, so this is what I want to say about the definitions of maximal and prime ideals. Now the first theorem that we're going to show that any ideal is contained in the maximal ideal, and for this I'm going to need Zorn's lemma, so maybe I start with a definition that allows me to formulate Zorn's lemma just in case you forgot what's the statement. So partially ordered set, I'm going to call this pose set, so this stands for partially ordered set. The pose set partially ordered set is a pair, so set P with binary relation less or equal, such that we have three properties. So first property is A is less or equal than A for any element A in the set P. Second property, the transitivity of this binary relation. So if A is less or equal than B and B is less or equal than C, and from this we can conclude that A is less or equal than C, and this has to be true for any A, B and C in the pose set P. And the last property is that if we have A less or equal than B and B less or equal than A, then from this we can conclude that A is equal to B. Again, for all elements in the P. So this is a partially ordered set. Now I can say what's a totally ordered set. So maybe let me separate this definition into three parts. So this is going to be the first part, the definition of a partially ordered set. Now the second part, the definition of a totally ordered set. So P is called totally ordered set if 1 is replaced by the another condition 1 prime. And this condition is a little bit stronger. It says that that A is less or equal than B, or B is less or equal than A, and this has to be true for any A and B in the P. So, and finally, the last part of this definition is the definition of a chain. A chain in a pose set P is a totally ordered subset. Okay, so why we need this definition? Well, we have the following lemma, which is one of the versions of the axiom of choice. So Zorn's lemma, and it says the following, that if every chain of a poset P has an upper bound as an upper bound, and then P has a maximal element. Okay, now to prove the theorem that any ideal I is contained in a maximal ideal, so to show this we only need to apply Torrance lemma, so we need to find an appropriate poset and the chain in this poset. So take a chain in this poset. So the proof is the following. We take P to be the set of all ideals in the ring R such that I is a sub-ideal of these ideals. Now of course the binary relation in this case is just the inclusion. So of course first observation that P is not empty. Well, at least I have element I in this P. So I is an element. Now if I take a chain, so if L in P is a chain, so then to say that there is a maximal element in P is the same thing as say that there is a maximal ideal containing I. So I need to use this lemma, and for any chain I need to find the upper bound. So let's take chain L, and the upper bound is the following. I just say that I consider K, which is the union of all the ideals, so all ideals J in this chain L. So then this K. So first of all, this is an ideal. Well, check this. Check that this union is an ideal. And in fact, this is the upper bound. So it's an ideal and upper bound. End of the proof. Now I just want to emphasize that this observation, this union is an ideal, is not a completely trivial observation. You cannot just say that a union of any family of ideals is an ideal. That's just wrong. But maybe I give you another exercise related to this question. So the exercise says the following. If you have two ideals in the commutative ring R, so then the union, which is not ideal in general, but the union is an ideal, if and only if we have the following conditions. If and only if, say, I is a sub-ideal in J, or the other way around, J is a sub-ideal in I. So the key observation here to show that this is actually an ideal is to look at the fact that this is not just a union of some ideals, this is a union over a chain. So they all embedded one into another. Okay. Okay, so this is our first little theoretical result. Maybe let's do some examples. Well, prime ideal which is not maximal. So give me an example of a prime ideal which is not maximal.
can take a ring of polynomials of two variables, and we can take, for example, x and y, and we can take the ideal generated by x, and the quotient ring will be just a ring of polynomials of one variable. That's not the ring.
Yeah. So in this case, if you take the quotient, this is isomorphic just to the ring in the variable, a polynomial ring over the same field k in one variable y. So I assume that k is a field. So if the quotient is a domain, it means that the ideal that we consider here is a prime ideal. So P is prime, but this is not a field domain, but not a field. So this ideal P is prime, but not maximal. Okay, in the second example, I want to show you that one ideal could belong to many maximal ideals. So maybe let's take the same ring, polynomials and two variables, and let's consider ideal I to be the principal ideal generated by some polynomial f. So in this case f is just some polynomial. Now, well, maybe for simplicity I want to assume that this field is not just any field, but okay, so the argument is actually the same for complex numbers or for general field. So I claim the following, that for any pair, say A and B, which is in the k squared, if you have property that A at this point is 0, right? So we can think about this f as defining a curve on a plane. So you take any point on this curve, and with this point you can associate maximal ideal, so MAB. So this is an ideal generated by x minus a and y minus b. Well, I claim that this ideal f is contained in all such maximal ideals. And if you can find many such points, for example, with complex numbers, you can definitely have a lot of such points on the curve. So you have a quite huge family of maximal ideals containing the given maximal ideal, containing the given principal ideal generated by f. And why this is so? Well, that is because you can look at this polynomial and rewrite this as in the following form. Okay, I use a minute to erase these two blackboards. Think why this is true. If you have the condition that f at AB is equal to 0, then this is true. Okay, any ideas how we can prove this?
Maybe we can divide the number f by x minus a stolbik. I don't know how to say it in English. I'm not sure.
Yeah, if you try to divide this, well,
No, stolbik. So I have some marker and it will be
well, when you try,
x.
yeah, but when you want to divide with the remainder, you want to have something called Euclidean ring, right? To guarantee that there is a division procedure. Well, what if you do the special case? What if A and B, A is equal to B and is equal to 0? Then I guess this would be a completely obvious observation. right? But if you don't have this situation, so then this is clear. But we can do the following. We can kind of consider the ring in two variables and just introduce new generators for this ring. We go from x and y to the x prime and y prime, and clearly this is invertible. So this is some automorphisms of the ring R. So automorphism of R. So essentially you go to the new generators of this ring, x prime, y prime, then this claim will be clear, but instead of x and y you use new variables, but then you can just rewrite everything in terms of x and y because you can invert this automorphism. And so you can actually observe that this observation is the beginning of the Taylor expansion, right? If you wish, you can drop this condition, then you just need to take this f, subtract this constant term, then for the rest of this you get this thing. And then you just repeat this procedure for f1 and f2, do the same expansion, continue doing this, and then you get the Taylor expansion for polynomials. So you can see that the Taylor expansion for polynomials doesn't require any analysis. You start with a polynomial, you get another polynomial. But maybe instead of x and y, you use different generators of the ring. Okay. So these were examples. Now we can also observe that the following is true. So every non-unit element of R is contained in the maximal ideal. Well, the proof is just one line. You take this x in R, x is not unit. Well, by the way, unit means invertible. So unit by definition is the same thing as invertible. So x is not invertible, or x is not unit. So then you consider principal ideal generated by this x. It is contained in some maximal ideal by the theorem, and that's the end of the proof. So any x definitely is contained in the principal ideal generated by this x, and any ideal is contained in some maximal ideal. So quite elementary observation. Now I want to give definitions. Well, we're not going to use this right now, but maybe it's a good place to give these definitions. So a ring R is called local if it has a unique maximal ideal. So in this case, people sometimes write pair R and M. So whenever you see this pair of a ring and ideal, so this means that this is a local ring, this is unique maximal ideal. So, okay, maybe again I split this definition into two parts. So this is the definition of a local ring, and also there is a notion of a semi-local ring. So a ring R is called semi-local if it has finitely many maximal ideals. Okay, example. So the simplest example of a local ring is the following. You again take a field. Now you consider formal power series in one variable, and you take the ideal generated by x. Okay? So here an element, if I take f in this formal power series ring, oh, this is just by definition an infinite sum. If you haven't seen this before, you can check immediately that you can take the sums of infinite sums, you can define products of these infinite sums, it will be a ring And here in this maximal ideal, we have, so f belongs to this maximal ideal. This means that the coefficient C0 is equal to 0 for the same expansion of f in terms of powers. And of course, you can generalize immediately this example into several variables. Okay. So next proposition. So let M be an ideal. So the moment this is any ideal, but this will be maximal ideal in a second. So if for any x which is in the ring, but not in this ideal, so in the complement to this ideal M, so if any such element is a unit, I can say if any such element is invertible, that will be the same thing. So then R is local and M is the unique maximal ideal. Okay. So let's prove a little bit more. So let's take an ideal I in the ring R. So if I have an element, so if x lives in this ideal but doesn't live in the given ideal M, right? So suppose I have such element, right? So then I know that any such element is a unit, right? So if x belongs to this complement, then x is a unit. Now I have a unit in the ideal I, right? This means that I is actually not an ideal but the ring itself, right? So when I have a unit, I hope this is clear. If something that I say is not clear, you can just ask me and stop me and ask me. Right here we have a unit, so it's invertible. I can multiply this by x inverse. I'll get 1 in the ideal, right? But if I have 1, the identity, I have any element. So that's why I have this implication. So it means that we can conclude that any ideal, which is by definition means any proper ideal, not by definition but by our convention, so any ideal is proper ideal. So any ideal is contained in M. And I claim that's enough to show this because, well, if I want to show that there is a unique maximal ideal, I take this ideal I to be other maximal ideal. It is contained in the given ideal M, so they coincide because I start with the maximal ideal. So there is only one maximal ideal, namely this ideal M. And by the way, if you want, you can take this proposition and apply this proposition to this example. You only need to show that if you take any element which is in the complement to this ideal, then this is invertible. But in the complement we have power series such that it starts with a non-zero term. Perhaps you've seen this exercise that you have a power series that starts with a non-zero term. This is invertible. It can be just explicitly you can explicitly compute the inverse of this power series by solving some system of linear equations for coefficients. Okay. So next proposition. So if M in R is a maximal ideal, such that 1 plus M are units. So this means that I consider all the elements of the form 1 plus something from this maximal ideal. So such that all these elements are units, then R is local. Of course, with the unique maximal ideal, which is this M. Again, we take some X which is in the complement to the maximal ideal. Right, since this is the complement to the maximal ideal, if I consider new ideal, which is M plus the ideal generated by this X, right, or I can think about this, I take all these possible sums of the form something from the maximal ideal, some element of the ring times X. Well, this is clearly an ideal. You can check this immediately, or you can just use the general property that this is an ideal, the sum of two ideals is an ideal. So, and this is definitely larger than M, because X is not in the M. So the only possibility for this sum is to be equal to the ring. Okay, now I can claim the following. I can take in this ring element 1, and 1 is an element in R, and for this 1 I can present this as a sum of something in the maximal ideal and something in the principal ideal generated by X. By the way, this is the same as principal ideal with one generator X. Okay, so 1 is equal to the Z plus YX. So here Z is in the maximal ideal M, and Y is any element in the ring. No, some element in the ring. Okay, now what I know that I have something of the form 1 plus something in the maximal ideal, then this is a unit, right? So 1 minus Z, which is the same thing as YX. So this is a unit. Well, if this is a unit, there is W in this ring such that the product of the W, Y and X is equal to 1. Or in other words, I can just say that X inverse is equal to the WY. Right? Just yeah, that's correct. So any element which is in the complement to the maximal ideal is in fact invertible. Now use previous proposition. So we proved this one. Okay, next proposition, which partially explains why working with the prime ideals may be a little bit more natural than working with the maximal ideals. So now we have a ring map and let me take Q in the S to be a prime ideal. Then the pre-image of this ideal is prime. Now before I prove this, can you give me an example such that pre-image is not maximal for some maximal ideal M? So preimage of a prime ideal is always prime, but preimage of a maximal ideal is not necessarily maximal. Yeah.
What if we is a ring map from Z to Z, and by and multiplicate by 2. So from Z to Z,
So
and the 2 is the maximal ideal in the ideal element. Yeah, and it's
what's the preimage of this ideal?
the problem is that it's not a ring map because
Yeah, that's also true. Yeah, multiplication by 2 is not a ring map.
okay.
Yeah, but you can modify this example a little bit and get the right example. What if you just take embedding of the integers into rationals? Well, this is definitely a ring map. But in the rationals, you have the zero ideal, which is a maximal ideal. But the preimage of the zero ideal is zero ideal. Well, in this case, well, because this is just an embedding, right? So the preimage of the zero, well, as ideal. In general, the preimage of the zero ideal would be the kernel of this map, but in this case there is no kernel because it's an embedding. So here, zero ideal is a maximal ideal, but in the Z, zero ideal definitely prime, but it's not maximal because the quotient by this ideal is not a field, but just a domain Z. Yeah. So I want to prove this proposition now in general. So the proof is the following. I look at this map F and take a composition with a canonical projection to the quotient. So I have ideal Q, so with any ideal I have a canonical surjection to the quotient ring, and let's call this composition F bar. So by definition, F bar is the composition of the I and F. Okay, now I know that the quotient S by Q is a domain. Now what's the kernel of the F bar? Well, we can compute this essentially by definition. So the kernel of F bar are all elements X in the ring R such that F bar of X is equal to 0. But notice that this is 0 in the quotient ring. So, and in terms of how I defined F bar, I can say this is the same thing as X in the R such that F of X is in the Q. So, by just looking at what we have, we can say that the kernel of the F bar, that's exactly F inverse of the Q. But now use the isomorphism theorem for rings. The quotient by the kernel is isomorphic to the image. So R, I want to take quotient by the kernel, but instead of I just write F inverse of the Q. And this is isomorphic to the image of the F bar, which sits inside the domain S modulo Q. Or maybe they coincide, but that's not important. So a subring of a domain is a domain. If we have zero divisors here, we will definitely get zero divisors here, so it's not possible. So this is a domain. And if the quotient ring is a domain, then the ideal is prime. Okay, and we finish the most elementary part about the rings, some reminder about the ideals, maximal and prime ideals. So the second section is about radicals. So definition. The radical of an ideal I is the following thing. So there are two notations. You can use this square root notation for an ideal, or you can use the rad of I notation. Well, I prefer the first notation because it's just a little bit shorter. But this is by definition all the elements in the ring such that some power of this element belongs to the ideal. Well, the way it is defined, it's only clear that this thing is a set. I claim that in fact this is an ideal. So the radical of an ideal is an ideal in the ring R. Well, I need to check a couple of properties. I need to take two elements in the radical, and I want to show that the sum is also in the radical. Right? So the question is, if I know that there is such some n, so the property that these two elements are in the radical means that there is n such that x to the n is an I, and there is also m such that y to the m is an I. How we can find the corresponding power for the sum?
Plus n plus 1 maybe, or
I think even minus 1 is enough. So n plus m. I think minus 1 is enough. Right, so we just use the binomial formula, and whenever we have some constant x to some power and y to some power, if you want to get something in the ideal, you want these two powers to be sufficiently high. So I think this will be sufficiently high. But you can check this. If I, instead of minus 1, I need to write plus 1, this also do the job. Now this is why this is closed undertaking sums, and for the products it's even easier. If x to the n is in the ideal, if I take a product and raise this to the same power, this is again in the ideal, and this is true for any a in the ring. So indeed, this radical is not just a subset, that's an ideal. Example. Let's take something easy. So let's take a ring to be integers, and let's take n to be some integer number, and consider ideal to be, well, in this ring any ideal is principal, so take principal ideal generated by n. So what's the radical in this case?
We have m equals some product of prime.
It's like they divided by prime, so divide it to divide
And radical y is an ideal generated by the product of the I in the total point.
Yeah, that's exactly right. So if it's not clear for you at the moment, I leave this as a little first homework. Think why this is so. It's actually quite easy observation. And of course you can do exactly the same thing for, say, polynomials in one variable. But if you have more than one variable, it might be a little bit tricky. Okay. Now I want to prove one important theorem about this radical, namely that the radical of an ideal is the intersection of all prime ideals containing this ideal. And to do this, I need definition, which is actually quite important in commutative algebra, but at the moment it will be just a technical definition that we're going to use in the next theorem. So a subset S in the ring R is called multiplicative if you have two properties. So first one is in this S, and the second, which gives the name to this notion, is that if x and y I in S, then the product is in S. So it contains one and it's closed under taking products. It's a kind of new notion. It's not related to the notion of an ideal, but when we discuss localizations of commutative rings, maybe somewhere in the March, maybe even in February, we will see that this is quite important notion for in general, because we can localize with respect to such multiplicative subset. Now, why we're interested in this notion right now? Well, that is because we have the following proposition. So let S in R be a multiplicative subset, and I in R is an ideal disjoint with the given S. So the intersection of the ideal I and S is empty. So then there is prime ideal P such that we have two properties. I is contained in P and P is still disjoint with S. Okay, so the proof is again based on the Zorn's lemma. We consider the set of all ideals containing the given ideal I and disjoint from S. We'll consider this set, use the same argument as our first theorem. You can conclude that there is a maximal element. So the set of all ideals containing I and disjoint from S has maximal element P. So I claim that this maximal element is exactly the P that we have in the statement of the proposition. Okay, so I need to show that P is prime. So claim P is prime. So in other words, I want to show the following. If I have two elements, X and Y, which are not in the P, then the product is not in the P, right? Clearly this condition is equivalent to the definition of a prime ideal. So let's show this. So first of all, I claim that if I start with two elements, X and Y, not in the prime ideal P. So I first observe that P plus, say, Rx, well, this is ideal, X is not in the P, so this ideal is larger than ideal P, which is a maximal element. So whenever I take intersection with S, it has to be non-empty, right? Because P is maximal, this is strictly larger, so the intersection is non-empty. And of course the same is true for the Y. Okay, from these two things together, I can conclude that if I consider the product and again take the intersection with S, I'll get something not empty. Well, I have an element in this first ideal which also belongs to the S, and I have element in the second ideal belonging to the S, and S is close to taking products, so I take the product, it's still in the S. So that's why I have this. Well, since S is multiplicative. Okay, but on the other hand, I can just look at this product and open brackets, right? So this thing will be not exactly equal, but at least I can say that this is contained in the prime ideal plus x plus r xy. Right, I've opened brackets, so product of something from the p and p will be in p, rx and p will be in p, ry and p will be in p, so the only non-trivial part will be this one. Okay, but from this I can immediately, well, if this set has a non-trivial intersection with S, this thing is even larger, so it definitely has non-trivial intersection with S, so x, y is not in the P. Because if xy is in the P, so this whole thing is just P, and the intersection with S will be empty. So otherwise, we get contradiction. Okay? Really clear? Questions? Okay, so that's kind of a little technical statement. Now the main theorem about the radical of ideals. So this next theorem, you know, maybe perhaps you heard that in commutative algebra there is an important theorem called Hilbert-Nullstahlen-Satz, which is the theorem about zeros. So this theorem also has some German name. I'm going to copy this German name on the blackboard, but I'm not going to pronounce this name. This is a name sometimes you can find in the literature for this statement. So at least it's saying that this is an important statement. And the statement is very easy to formulate. The radical of any ideal is equal to the intersection of all prime ideals such that I is inside these prime ideals. Okay, so first step is the following. I want to show, so first claim is that the radical is contained in this intersection of all prime ideals containing the given ideal. So get inclusion in one direction. Okay, suppose I have x in the radical of this ideal, so it means that there is some power such that x to the n belongs to the ideal I. Now, if I assume that this ideal I is contained in some prime ideal, I can conclude that actually x is contained in this prime ideal. Well, that is because P is prime. And if you know this property for the two elements, but of course you can derive this property for product of finitely many elements. So in particular here you have a product of finitely many elements which happen to coincide. So if some power belongs to the prime ideal, then this element belongs to prime ideal. Is it clear what I'm saying? Do I need to explain more? You can do this by induction. Think about this as x and times x n minus 1. This belongs to the prime ideal. If x belongs to the prime ideal, you're done. Otherwise you get this part belongs to the prime ideal. You just continue by induction. Okay, so what we have here is actually the proof of this claim. Right? Because whenever I take an element in the radical of an ideal, it belongs, and whenever I have a prime ideal containing I, this x belongs to this prime ideal. So it belongs to the intersection of all such prime ideals. That is true for any P such that I is contained in P. So then x is an element in the intersection Now the second step is not to show that there is inclusion in the other direction, but instead I'm going to take x, which is not in the radical, and show that this is not in this intersection. So X is not in the radical. Now for this part I need the previous proposition. That's why I proved that proposition about the multiplicative subset. Now take S to be the multiplicative subset 1, x, x squared, etc. all powers of x. So this S is multiplicative subset. Actually, this is the only kind of multiplicative subset that we need in this proof. So we proved something for quite general situation, where you have just any multiplicative set in the theorem. We need only this particular multiplicative set and generate by one element. Okay, X is not in the radical. It means that the S is disjoint with the ideal. Now take, by the previous proposition, take P such that we have two properties. I is contained in the P and P is still disjoint from the S.
X is not in the radical.
X is not in the radical, thank you. Yeah, so if X is in the radical, I proved everything. If X is not in the radical, I want to show that the X is not in the intersection of all prime ideals. So for this I take this specific multiplicative subset. By the previous proposition, I find the prime ideal containing ideal I and disjoint with the multiplicative set S. So, but if I can find such an ideal P, right, which is disjoint with S, so then from this is actually I can conclude that X is not in the intersection of all such prime ideals. No, because this is not in this particular prime ideal, and this particular prime ideal contains I.
So this intersection of E and S is empty.
It's empty. Okay, I think that's all we can do today, so let's stop here and then we continue next time.